So for today's lecture, we'll talk about deep learning model efficiency. So we've all witnessed the great success of deep learning, right? So here, this figure shows there's a different type of neural network architecture has been developed over the years, and there's a common trend is that the number of parameters has increased significantly. And also, this comes to the challenge of the increasing of compute, right? So here on the x-axis is the year, right? So which year these deep neural network has been developed, and on the y-axis, this is the compute need or the number. You can also find the number of parameters for the corresponding network. So you can see that the complexity has been increased a lot for some of the large models, right? So now we know there's this kind of large language model like a GPT, right? So they can be as large as 20 billions of parameters. So you can imagine how much compute we need to train such a large model to generalize the task. And just to give you a more concrete idea, right? So here is a table to show a very detailed comparison of some of the classic convolutional neural network from the simple LeNet, AlexNet to the efficient network. So here list the architecture, right? How many conv layers for different networks, and the number of parameters, right, for different networks, and also the number of compute, right? So this MAC is the multiplication and the summation, right? So these kind of basically give you a sense, right, how much floating point operation the particular network is required. Okay, so the general trend is that the network is getting larger and deeper, but that requires a significant computing resource. But in our real world applications, right? So now we are living in the era of AI. So a lot of devices, especially those edge devices, right, IoT devices, has some sort of computing power, right? Like the smartphone, smart surveillance cameras, robot drones, right? So they all have some computing capabilities, but it's not very powerful as the commercial GPU or the GPUs in the data center or high performance computing center, right? So some of the large deep learning models cannot be readily deployed on these resource limited devices. For one thing is the memory cost and the computational cost is just too high. These devices is not able to host, is not able to deploy such model. Okay. So we need to come up some of the solution to address the issue, right? So how can we deploy these, deep learning model on these resource limited devices, right? So people have, research has been thinking about several ways to come up with efficient neural networks. So here shows like 4 different ways we can design efficient neural networks so that they can be deployed on these resource limited devices. One approach is we can do network pruning, right? Basically, we can kind of trim down, right? Reduce the number of parameters in the network, right? So usually the deep neural networks are highly over-parameterized. Some of the neurons, they are kind of redundant. They perform similar tasks, serve the similar process. So we may remove some of the redundancy in the network so that we have a slimmed version or a much smaller network, right, in terms of the parameters, and also reduce some of the compute and memory footprint. So that's the network pruning. Another is we can think about some of the the operation is in the classic deep neural network, right? So one is the most popular is the convolutional neural network, right? So maybe we can rethinking some of the design, right? Come up with some efficient operations to achieve network efficiency, right? So this is also very interesting area, and people have design some of the efficient network architectures that is specifically for mobile applications. And another perspective we can think about is to reduce the precision, right? So normally we consider the full precision, right? The machine precision, that is the 32-bit floating point operation. But we can maybe we don't need this full precision, right? So we can quantize or reduce the precision maybe into 8-bit, 4-bit, right? So this low bit resolution, or even go to the very extreme case, right? We have this binary network, right? So you have the weight and activation or binary, right? So 0 or 1, or either -1 or +1, right? So these are the extreme case, the binary network. And the last category is the knowledge distillation. So basically we can have a large network. We can call this as a teacher network, right? So usually this is a pre-trained network. We can leverage these kind of public available pre-trained network. But in our resource limit application, right, we cannot deploy these large network, right? So what we can do is we can still, deploy a, much smaller network, right? We call this student, right? Much smaller means maybe the number of parameters, the number of total compute, right? Floating point operations is much smaller than the large teacher network, right? But we still want the student network to perform, at least very close to the teacher network, right? Because we know if we don't do some of the, process, the capacity, the learning capacity of the student is limited, right? So this knowledge distillation, the notion is that we want to kind of transfer the knowledge from the large teacher network to the student network, so that the student is able to mimic the performance of the teacher network, but enjoy the the computation and the memory efficiency, so they can be deployed on these resource limited devices, right? So that's the method of a knowledge distillation. So in this lecture, we'll talk about all these different type of approach to achieve model efficiency for these kind of resource critical applications. Okay, so let's first look at this one, the efficient network architecture, right? So we will look at a couple of very classic efficient network architectures, and these has been used a lot in some of the mobile applications or edge computing. Okay, so the first network we look at is the called MobileNet. Okay, so they specifically designed for mobile application, right? So they want to run the deep neural network, the CNN network, on the mobile device, the cell phone, iPad, so you can do like object detection, face recognition, right? Maybe also do some image classification, image enhancement, something like that. Okay. The innovation they have for this MobileNet is this depth-wise convolution filter and the point-wise convolution. So to reduce the number of computations as compared to the standard convolution, right? So here shows the standard convolution, right? So this is the one filter of the standard convolution, right? So we have the spatial dimension, right? Height and width, right? dk by dk. So this can be 3 by 3, 5 by 5, right? So and the fm is the number of channels, right? How many channels it has. This should be match the input feature, right? So if the input feature map has m channels, so the channel dimension for this kernel should be also equal to m, right? And we typically apply m different filters, right? So we wanted to learn different patterns from the data, right? Different orientations, directions of the edge, right? And also the combination. So this is the standard convolutional filter. So let's look at, for the standard convolution, right? How many compute it will involve, right? So we are talking about specifically interested in the multiplication operation, because that's the most time consuming operation in the actual, when we implement the hardware. So, okay. So here we have this feature map, right? So let's consider this feature map have spatial dimension of df by df, right? The height and width, df by df, and also the channel dimension is m, right? So have m channels, and if we apply a classic or conventional convolutional kernel, right? We specify the dimension as well, right? dk by dk, and to match the input feature map, it has to have m channels, right? To match the channel dimension. Okay, so we do this, right, as a sliding window fashion, right? We put this filter slide across this entire feature map, and we will generate the corresponding output, right? Okay, so if remember, right, so at each position, right, this filter, we have how many multiplications? We have we have this df by df times m, right? So if we slide across this entire feature map, right? So the input, we have these many multiplications, okay? And so for one, because this will generate one scalar, right? So if we specify the corresponding output, let's say it's dg by n, right? So this will have we will time this many of operations, right? So you can compute how many multiplications it requires to do this conventional convolution, okay? So you can also do this decompose into different stages, right? So how many multiplications for one position, right? So that's dk squared times m, right? So one position, we have these many multiplications. And if we, do this one kernel over the entire input, right? So that's we will have dg squared, right? Assuming we have the output of feature map of dg by n. Okay, so that's for one kernel over the entire input. And if we apply, right, n kernels, right? So n this type of filter, dk by m, right? This n of this kind of kernel, we have this many of multiplication. So we can compute that, okay? So let's look at the depth separable convolution. So this MobileNet proposed this depth-wise separable convolution. It can consist of two stages. One is the depth-wise convolution. So we can consider this as a filtering stage. And the second stage is the pointwise convolution. Okay, so this can be considered as a combination stage. Okay, so the objective is, by doing this depth-wise separable convolution, we want to reduce the computation, right? In particular, the number of multiplications for this convolutional operation. So let's look at the first stage, right? This depth-wise convolution. So instead of doing this m channels, right? So like the conventional convolution, now we will do just a single channel, right? So this dk by dk. So we have this m different kernels, okay? So we are basically applying this individual, right, dk by one kernel, to individual channels, right? We are not looking at m channel together, right, like the conventional convolution. So we basically look at each individual channel individually, okay? We apply one to generate the corresponding output, then apply the second to the second channel and generate the second feature map, okay? So this is a kind of like a graphic illustration, right? So let's assuming the input has three channels, right? Though we have these depth-wise convolution is we apply these three convolutional kernels, each has one channel dimension, and we apply this across each individual channel to generate the corresponding output, okay? So we can still generate, right? So if we have specify m of this kind of channels, right, or filters, we will generate the output has the channel dimension of m, okay? So we can still do this in this kind of, for each of the input feature channel to generate the corresponding output has dg by dg dimension, okay? So here, just to, if you want to simplify, you can consider dg and df have the same dimension, right? If we consider padding, right? We are not reducing the we don't have any stride, right? Or stride equals to 1, we have the same output dimension, right? So you can view dg equals to df for simplicity. Okay. So, and now comes to the second step, which is the pointwise convolution, right? Because in the first stage, we apply these filter on each individual channel, right? But for the conventional convolution, we look at all the channels together, right? We are able to look at all these information from different channels. But in the depth-wise convolution, we treat channel each individual separately. So now we want to kind of mix these information from different channels, right? So that's why the second stage is doing this kind of combination stage, right? Trying to combine the information that is reside in different channels, right? So here we have a spatial dimension of 1 by 1. So basically we at the 1 pixel location, and we are interested in, aggregate information across the channel dimension, right? So we have the filter shape have M channels, right? We want to aggregate the information from the channel dimension. Okay, so that's the combination stage. And we can do this for specified M filters and do this kind of pointwise convolution to achieve this kind of information mixture from different channels. Okay. So we can again compute the total number of multiplications for these depth-wise separable convolution. And so I'm not going to do this step by step, but this is basically give you like how many multiplications it has for the depth-wise separable convolution. And we can actually do a comparison, right? To compare with the standard convolution and this depth-wise convolution in terms of the number of multiplications. And this is, this is the ratio, right? For the depth-wise separable convolution and the standard convolution. And as you can see that this definitely reduce the number of computation a lot, right? So if we just plug in some numbers, right? Typical numbers for the dk is the spatial dimension of the filter size, right? N is the number of filters. And we can see that, right, compared to the conventional or the standard convolution, right? So this depth-wise separable convolution is actually like 11%, right, in terms of the number of multiplications. So that's a significant reduction in terms of the computational cost. Okay, so that's how they achieve the efficiency, to cope with some of the resource limitations for mobile applications. Okay, and in this table, they also do comparisons with some of the standard network, right? With standard convolutions, right? These GoogleNet and the VGG, right? So in terms of number of parameters here, and also in terms of the computation, right? How many multiplications and additions, right? So this MobileNet is able to significantly reduce the computational cost. And at the same time, right, if we look at the ImageNet classification accuracy, the performance actually does not suffer a lot, right? If we look at this VGG network, it only reduced the accuracy by less than 1%, right? But in terms of the saving of parameters and flops, right? So it has significant reduction. So that's the advantage of these efficient network of MobileNet. Okay. The second efficient network is called a ShuffleNet. So basically the idea is very similar. So instead of considering all the channel dimensions each time for each individual convolutional filter, so the way now they are doing is they divide these channel dimension into separate groups, right? So for the depth-wise separable convolution, you can consider there are actually each channel is considered one group, right? You have n channels, then you have n group, right? But this may be do not consider all these channel dimensions, but you can using pointwise convolution to mitigate that. But this may still can cause some of the performance drop, right? So what they do is instead of just considering each individual channel as a group, they consider maybe a couple of channels as group, right? So for n channels, you can specify G group, right? And then within one group, you have n over G number of channels, right? So that's how they do the grouping of the channels. And then they just apply the convolutional filters for each of the group, right? Instead of considering all the n channels, the convolutional filter will apply within the group, okay? So here, just an example, right? So we have all the channels and divide this into 3 groups, and we apply convolutions within each of the group. As you can see here, this purposely using different colors to indicating different groups. So again, among different or between different groups, right, there's no information flow into different groups. So this may not be a good idea. So that's why they come up with this kind of shuffle operation, right? So after this group convolution, they want to basically shuffle the channel, right, to kind of mix the channels from different groups, so that when you go to the second group convolution, you are able to, for each of the groups, they have some information that is coming from different groups, right? So the information flow can be freely flow into different groups. So that's their channel shuffle operation. And there goes the name of ShuffleNet, okay? And the third network, the latest work, CVPR 2020, they propose this ghost network. So this is inspired by their observation is that, if we look at the convolutional feature map, right? So these are the different feature maps from the conv layer. And you can see some of the feature map are very similar, right? So this green box, right? So they are very similar. And this red one, they are also very similar. This blue one, they are very similar, right? So you can see some of the redundancy in these feature map, right? So so the inspiration is that, maybe we don't need these many different kernels or filters, right? We can reduce the number of filters, and we can just apply some of the, cheap operations, right? Because if you look at, look this pair, right? The red box, this may be just adding some of the values, right? So this is more brighter than this one, right? So maybe we're just adding some of the values to this feature map, we are able to get this, right? Rather you apply a separate filter to generate this feature map, okay? And this one may be also similar, right? We're just adding some random values, right? Or just very simple linear operation, maybe multiply by a coefficient, we are able to get a separate filter. So that's their intuition. And based on that, they set a set of basic filter, right? So this is a basic set of filter, and they can generate a bunch of feature map, right? And now instead of doing separately or adding more channels, they using some so-called cheap operations, right? Basically linear transformations on the original convolution, and to generate the corresponding feature output, right? So in this case, the computation can be reduced because we are not doing any of the additional filter to generate the feature map, okay? So that's called the GhostNet. And they also compare their proposed GhostNet with the previous developed efficient network, right? The MobileNet family, right? So this V2 and V3 version, and also ShuffleNet. So they show this graph, right? So if we look at the vertically, right? If we have a specified number of computation budget, right? The 200 million flops, and under this computation budget, they are able to achieve the best accuracy, right? If we only look at vertically, okay? But we can also look at horizontally, right? So if we want to achieve a target accuracy of 70% accuracy, right? So for their GhostNet, they are able to use less computation cost to achieve this, okay? So by the way, this is this kind of accuracy versus the flops is the typical metric people look at, right? When they evaluate the performance if they are targeting at developing this efficient deep neural network. Okay.